Hello, everyone. So my name is Gary Nakanelua, and this is Steve Hastings over here. And today, we're here to briefly share a use case for an experiment that we've been running with Spark and drones. So if you'll indulge me for a few moments before we jump into the tech, I want to give a bit of a background behind the inspiration for this experiment. Then, Steve will share some of the incredible work that he's done that's helped push the experiment farther. Now, and then at the end, how many of you all visited our booth down in the exhibition hall? Yes, that's awesome. So at the end, we will be giving this very drone away, which, by the way, we use this very same model in our experiment. So you can try this out at home. So here we are, almost at the end of the summit, and it's been awesome, right? This is actually our third year coming over to Spark Summit, and it's pretty darn cool what people and organizations are doing and achieving with Spark today. So, I mean, conversational artificial intelligence, genome sequencing, like detecting water on lunar craters. Like, seriously, that's awesome stuff. So hopefully at this rate, I imagine at next year's conference, someone will be presenting the use of Spark to power an early version of the Oasis. And for those of you that may not have seen Ready Player One, the Oasis is a fully immersive virtual reality game that everyone in the world practically lives in. And ironically, that future and that world was actually created by someone that's incredibly nostalgic about the 80s, which I can relate to because as a child of the 80s, I grew up dreaming about a future where people walked around with power gloves and virtual reality goggles everywhere they went, right? Now, as managing director of experimentation at Blueprint, I have the distinct privilege to lead a team that is constantly experimenting with emerging tech. And we do this to accelerate our customers' digital transformation strategy and help them discover their next big thing. So over the years, we've learned that when people imagine the digital future, there are three common motivations. Coolness, for the Parker Lewis Can't Lose fans out there that remember, right? We have achieved coolness. Elimination, and finally connection. When it comes to coolness, drones rank pretty high, at least I think so. So when I first caught wind of consumer drones, I had to have one. And so after breaking and losing a few, it didn't take long for me to get into competitive drone racing. This is one of the races I was at, and the way it works is you strap goggles to your face, and using the front-facing camera of the drone, you fly laps through an obstacle course. Depending on the drone and the course, we are talking speeds in excess of 100 miles an hour. And if you want to get a feeling for what that is like, you can actually try this out for free on a drone racing simulator. The second motivation is elimination. And from how you work to the way you enjoy your free time, elimination has become synonymous with convenience and an easier life. As a child, I didn't grow up with a computer in the house. My father was a well-known mechanic in the small town I grew up in, so our time was spent tinkering on cars and rebuilding engines. Something that always amazed me was how my father could troubleshoot car problems without actually touching anything in the car. So while the car was running, he would move around and kind of get in that little pose and glare at the engine or turn his head to listen. Then he'd say something like, "Oh, looks like it's the alternator," or "Oh, you're losing compression," something like that. I can't do a very good impression of my father, but it was a diagnosis that at times actually proved correct. And it was just fascinating to me how a couple of our most basic senses, sight and sound, could be used to diagnose such complex machines. Inevitably, however, the digital future would end up in our driveway. A good friend of my father's comes to the house with this brand spanking new Pontiac Grand Am. It had electronic fuel injection and this computer that allowed mechanics to connect up a diagnostic machine and instantly get information from all the sensors connected inside. This would eliminate the need for mechanics like my father to spend hours or even days troubleshooting a problem. Now, this is standard today, but back then this was blasphemy in my father's eyes. Finally, For some, the future is about connection, right? This can take many forms, but a common thought is to slap sensors on everything and get them connected to the internet, right? From refrigerators to your toothbrush to trash cans to even our bodies, right? We want to connect all the things. This is Chris Dancy. I was introduced to him at the Think Big Festival a few years ago. He is considered the world's most connected human, using, embedding, and surrounding himself with over 700 sensors that include everything from respiration sensors to a headband that measures his brain signals. If it can be connected and measured, this guy is doing it. And there are those across a variety of organizations that look at him and go, oh my gosh, I want to do that with all my equipment, software, and processes. IoT everywhere. Now, each of these motivations are individually applied into new ideas every day. But I want to present a simple hypothesis to you. If no single motivation is capable of truly ushering in digital transformation, then applying all three together is necessary. Which brings us to the genesis of our autonomous drone experiment. As a technology, drones are actively being used in a variety of verticals, such as agriculture and the oil and gas industry. In fact, this video footage captured from a drone flying around a remote oil rig site in Midland, Texas. And what you'll notice is that the drone can get above and into areas given a different operational perspective of this rig. So it started with a question. How might we advance the use of drones in an oil rig site? Now, many upstream oil companies maintain a catalog of multiple oil rig sites, so engineers will be assigned specific rigs to inspect. However, these assignments are often based upon schedule, not need. So as a result, small problems can be left to grow into big, expensive problems because inspection won't happen for many days or weeks. Again, we ask a simple question. How might we eliminate the need for scheduled inspections of an oil rig? Now, the previous scenario may sound archaic, but truthfully, oil rigs have undergone significant technology advancements. But one particular area grabbed our attention. Nearly 93% of all land-based U.S. oil rigs have some level of sensor and telemetry data collection enabled. However, on average, only 80% of the operational state of the rig is actually enabled for telemetry. So, yet again, we ask a simple question. How might we get connected to oil rig data that isn't currently available? Taken in aggregate, our ideas for answering these questions can be applied to our theory about digital future motivations, thus evolving into a framework that allows us to very quickly determine the potential of our experiments to bring about true digital transformation. Which brings us to the big idea. What if a drone could run a pre-programmed oil inspection route and using audio and video feeds proactively identify potential issues? This would eliminate the need for strict reliance on scheduled site visits and get oil rig operations connected to data they wouldn't otherwise have access to. Which brings us to our experiment execution. Typically, drone flight requires line-of-sight operation by a licensed operator. While a number of higher-end drones enable flight programming, we quickly learned that the success of those flights is dependent upon a clear flight path. So we had to figure out obstacle avoidance. So armed with real-time data and video streams from the drone, we opted to leverage Spark and machine learning to process the data and enable the drone to detect obstacles, autonomously adjust its flight path to avoid those obstacles, then reorient itself back on the pre-programmed route. Now, inspired by the way mechanics can troubleshoot problems by simply looking and listening, we started experimenting with anomaly detection using video and audio streams from the drone. So, how did all this turn out? I personally would love to fly this and show you all, but it turns out there's like a lot of legality behind that. So we put together a little video for y'all so you can see this. And what you're seeing, what it was flying around there at the end was a 3D printed trebuchet that we did because we're building a much larger version of a trebuchet in our lab because we wanted a completely mechanical device to be able to run our experiment against. Now, physical drone experimentation isn't without problems. For one, because we were using a consumer drone straight off the shelf, the battery life was on average 10 minutes per charge. Partially solving this problem would be as simple as we just got other battery packs. However, the optimal time to actually test was when the battery power was about above 80%. Else the drone would exhibit less than ideal behavior, which leads us to the next problem. Drone experimentation is destructive. This is in our lab, and as you can see, we crashed our test drone many times. In fact, we crashed it over 70 times as we continued to get everything dialed in. So we had to find another slightly less destructive way of training and testing our obstacle avoidance models. Now, there are a few options available. There's like the drone simulator that I shared with you previously. But the truth is, between you and I, we really wanted to try something cooler. So, like Ready Player One, the answer lies in a video game, specifically Doom. And so here to talk about some of the deeper experimentation that has gone on, I present Steve Hastings.
Hi, thanks everybody. Thanks, Gary. So, get started here. So first off, I'm going to summarize what I'm going to talk about today. So first off, I'll introduce our learning environment, which is based on Doom. Then I'm going to talk about our experimental setup, what we actually did. Then I'm going to talk about the learning iterations that we went through, the results, and an analysis of how this relates back to our actual goal of piloting drones in complex environments. Then I'm going to talk about some ongoing research that we're doing currently at Blueprint around this very same topic. So, surprise, for those of you who may have figured it out, this is a deep learning talk. But the point of this talk is not to be a technical deep dive on deep learning. It's about a use case. So I'm going to try to stay out of the weeds of the deep learning and just talk about how what we did relates back to the drone. That being said, if you want to hear more of the technical details, come find me after this talk. All right, so some of you may be aware of this program. It's called VizDoom. It was created as an AI research tool. It uses an open source version of Doom and provides programmatic bindings to it in Python and a few other languages. And this is really good for what we're doing because we can utilize all the research that has gone into VizDoom and also all of the features of Doom itself, like map building. On the right there, you can see a screenshot of a Doom map builder where they're building a pretty complex map. All right, so why do we use VizDoom to experiment? Obviously, playing Doom is not the same as flying drones, but it is fast and efficient to run. There's a bunch of research using it in deep learning and deep reinforcement learning. It's widely customizable, like I said, about Doom maps. And there's useful parallels to drones. And I promise I'll explain that bit in a little bit. Okay, so our setup for this project was we've got a large circular map in Doom. And we have randomly spawned creatures that are trying to attack our friend. And our friend is going to try to walk around and avoid the creatures who are moving towards it and try to do that as long as possible. So this is actually a pretty cool proxy to a drone situation because it provides a complex environment where there's both static obstacles, like the walls, and dynamic obstacles, like the creatures. And the dynamic obstacles, the creatures, are actually behaving based on the behavior of our friend here. They're basically chasing him. Okay, so how are we going to model this? We used actually a pretty simple deep learning network, a deep Q network. And it basically takes the input from the frames, the pixels of the video game, and passes them through a couple convolution layers and then a couple of fully connected layers, and then it decides on an action. And the action is kind of the key here. A Q learning, for those of you who aren't aware, is basically it takes a current state of your agent, in this case our friend playing Doom, and tries to maximize some sort of reward, which you, as the person building this model, get to define. And they maximize that because whenever you're in a state and you take an action, you're going to get some sort of reward. It might be positive, it might be negative. And so the process of training these kinds of models tries to figure out for each state what is what's the best possible action you could take. Now the real innovation here with the deep Q networks is you're using the deep learning models to reduce the state space. You could imagine that there's nearly infinite possible different frames. The deep learning here reduces that to a manageable state space. So here's our first attempt. We just sort of trained that model, just saw what it would do. And here we have a video. So as you can see, our friend is kind of wandering about, and he's not doing a terribly great job. His health is ticking down. And he's going to get over here to the wall. And I like this one because it reminds me of like an insect crawling along the corner of your wall, if you will. And eventually he dies. He will die in just a moment. Oh, come on. Oh, all right. Okay, so what happened here? Our friend doesn't have 360-degree vision. If you recall back to your high school biology class, you might have seen a diagram like this on the right. Different animals have different fields of view that they can see. Our friend, since he's modeled after a human, only really can see in front of him. So anything that's behind or to the side, he doesn't see. And if you were paying attention during that video, you saw situations where you could infer, based on watching the video, that one of the creatures came up behind him and just started attacking him. And he didn't know how to prevent that. So this brings us to an interesting idea called partial observability. So in these kinds of situations, which would include a drone, which maybe only has one camera pointing forward, you need to be able to see the entire environment. And deep reinforcement learning networks of this type will actually help you out there. So here's our second iteration. And this one we trained a little bit longer, and it has a very different behavior. So as you see, our friend is just wildly spinning around. And if you look careful, he's also backing up at the same time. And now he kind of gets stuck on the wall. And he's done. So this one actually, he lasted a shorter period of time than the first one. So this was actually worse. So what happened? Our friend seems to have prioritized just crazily spinning around in order to see the whole environment. Theoretically, this would allow him to act on the creatures that he sees in an environment, but he didn't. I don't know why. But there's two ways which you might go about fixing this. One is to add a recurrent layer into your network. I didn't do that for this talk. Instead, I tried something different. I tried reward shaping, which basically allows you to customize the reward that your agent is gonna get according to his action. And in specifics, for the next video that I'm going to show, I prioritized him walking forward. So he got a bigger reward if he moved forward. Now, reward shaping also allows you to add domain knowledge into your model. So, in the picture here, we've got some sort of hydrocarbon pipeline. If I just put a drone out there and said, hey, avoid obstacles, it could just sit there, hover above the pipeline, and it would be perfectly fine. But that's not going to be helpful to us. We want them to be able to explore that pipeline. So by explicitly rewarding that kind of moving around the pipeline and exploring it, we're going to get a better outcome for the actual drone use case that we're talking about here. So let's try this one. So now I've reward shaped, and he's going to prioritize, hopefully, moving forward. And that is what we see. But he actually, just by adding in that reward shaping, he also seems to be better at avoiding enemies. Because although he's prioritizing moving forward, he doesn't only move forward. There's still penalties if he was to charge headlong into an enemy. So like right here, he backed up, and now he's turning, and he's going to run away. And this guy actually lived the the maximum duration of this episode. So this one was actually pretty good. These things are fun to watch. Okay, so let's summarize what we learned here and how they apply to drones. So even simple neural networks, I mean, this was not a super complex neural network, but even it, trained with reinforcement learning, led to pretty good behaviors based of our friend. He was able to avoid the creatures pretty well, and he utilized the walls to sort of help him out there, and stuff. So that's pretty cool. The other learning is that we need to account for partial observability. And like I said, we can do that in a couple of ways, and I chose one here. There's definitely others. And then the final one, and I think it's kind of the biggest one, is reward shaping can help build a better model, and it can also help you inject domain knowledge about your specific problem that you're trying to solve into your model. Usually people talk about how deep learning models just total black box. You don't know what's going on. You just feed it the data, and then it's going to do whatever it does. In this way, by using reward shaping, we have a way to actually inject our own domain knowledge into it. So I think that's pretty cool. Okay, ongoing research at Blueprint. So we've got a couple things that we're currently researching around this experiment. So one is using genetic algorithms to train our models in a distributed fashion. That's kind of just a general thing that we're interested in. Another one is apprenticeship learning. So what this means is in reinforcement learning, your agent, our friend here, has to, for part of its time, just make random movements and see how that turned out. Sometimes they'll turn out good, sometimes they'll turn out bad. An alternative to this is actually apprenticeship learning, where you have potentially a human expert, in this case playing Doom or flying a drone, and your model is able to identify from how your human expert is playing, it's able to identify the actions that it should take based on different state. And a cool side note on that is that a while back, like 20 years or so, there was an interesting paper that came out that used apprenticeship learning to do helicopter flight tricks. So that was pretty cool, and that relates to drones. Number 3 is real-world reward shaping, just continuing to bulk up on knowledge of how to use our domain knowledge to affect how we're prioritizing our drone's behavior. And then 4 is latency. So you could embed the runtime of these models on your drone, or you could stream your information from your drone back to some sort of centralized place and evaluate your deep queue network in that centralized place, and then send back the action that drone should take to it in the field. That's going to impose a problem because you're going to be acting on stale state, right? There's going to be a round-trip cost of sending the frames or whatever information you have back to the centralized server. But that's going to be important if we want to be able to run multiple drones that are as lightweight as possible and as are consuming as minimal power as they can. You're going to want to send that information back to like a Spark cluster or something and run your model there. So that's that. Also, we're hiring, so. And Gary stuck in a QR code and a link here talking about how to get started on some of the experiments we've done. So go ahead and go to that link or just explore it, have fun. All right, and finally, maybe the best part of the show is it's time to announce the winner of the drone. And for that, we've got Garen over here, and he's gonna come up and do a very cool random number generator. I think it's based on blockchain.
It's probably also worth noting that we're injecting a little bit of chaos into this because the idea for this came like, I don't know, like what, 12 minutes ago? Something like that. So also in case you all may recognize Garen, he was a speaker for a session yesterday all about avoiding potholes with Python and Spark, yes? So the idea is everyone that came to the booth, we scanned you and you were knowingly or unknowingly, hopefully knowingly, entered into the drawing for this drone. And so that entire list has been exported out, and now Garen's going to actually run this on Databricks to select our winner. Oh, drum roll. Yeah, there we go. Green is good. And our winner is... I don't know how to pronounce, let me see. Martin, I have a really long last name as well, so I'm not even gonna... Is Martin in the room? You didn't have to be present to win, so Martin, you are, if you're watching this, I hope you'll be watching it later, you are the winner of this very drone, so we will ship that out to you. And yeah, so want to thank everyone, and now we've got 2 minutes for questions, and of course, like Steve noted, you can always come and find us afterwards, and we'd be happy to dig in deeper.
For questions, please come to the microphones in the middle of the aisles.
Hello.
Hello.
One small question. All the research that you are doing, you need to have a specific drone, or you can use whatever drone chip that you can buy or whatever?
It's a great question. One of the reasons we chose this, we have a few different drones that we have around, like DJIs and things, but one of the things we liked about this, it was relatively low cost, and we had a pretty good idea that we were going to be running this thing into pretty much everything we could. The other thing is that programmatic access to this drone proved to be incredibly easy with like Python or Node. So it shortcutted some things for us. So costs and just ease of programming was our choice.
Okay, thanks.
You bet.
Thanks for the talk. I was wondering your results with the actual drone. Did you run the deep Q network with the drone at all?
So, and Steve can go into a little bit details, but as far as where we're at right now, this is still an ongoing experiment. So I just need to put out there, this is by no means production ready. It is held together with duct tape and baling wire. But what you are seeing, in that there is no like video edits to make it look like it is actually autonomously detecting. What the video doesn't show is that the obstacle we put in its way is the wooden trebuchet that we're building. So it needed to avoid that to be able to run its site inspection on the mini trebuchet that we had on the stand. So it is fully functional and processing, but it follows a very certain path that it knows very well, so there's still a lot of work to be done.
So were
Please
you
give them
guys-
another big hand.